So so what I will talk about is these two regimes that can be observed in very deep neural networks, and using how we can use the neural tangent kernel, the NTK, to understand aspects of related aspects of neural network architecture, such that normalization, so for example, batch normalization or layer normalization, and then other effects such as checkerboard artifacts and boundary artifacts in neural network. So because the NTK plays a very important role in this talk, I will first start by introducing the NTK quite rapidly, the basic results related to how the NTK describes convergence in deep neural networks. And then using this first part, I will then explain what we proved about this freeze and chaos regime. So first, let me introduce the type of model we're looking at least at first. So we will look at deep, fully connected neural networks. So we have L plus one layer, numbered from 0, the input layer, to capital L, the output layer. And each of these layers has a number of neurons NL. And the activations are defined recursively according to this formula. Maybe it's the typical definition. The only specific case is when we define the pre-activation. So the pre-activations of a layer are the activations before applying the nonlinearity. We have these scalars in front. So this square root of NL on the bottom, it just makes sure that, because we will be studying neural networks when the number of neurons in the hidden layers grows to infinity. So we need to have this scalar to rescale everything well. And then the other thing is that we have this square root of 1 minus beta squared and this beta on the other side in front of the bias term. And this is what we call the weight bias balance, beta, between 0 and 1. And the reason why we have to take this into account is that we will consider very deep networks. And for very deep networks, as long as we have, with this renormalization in front, with the scaling in front, as long as the nonlinearity that we use satisfy this standardized property, then the variance of the activation will remain 1 for any depth. So that's just the setting, so that considering very deep networks makes sense, at least mathematically. Otherwise, you would just observe some an implosion or an explosion of variance, which are not particularly interesting. So that's this few modification that we do on basic fully connected neural networks. And then the other important thing is that we define this network function as the function that maps the input to the pre-activation of the last layer. So we stop before the last nonlinearity. That's the model of neural networks that we'll consider. And so the first result, so the NTK is a kernel that describes properties of convergence of neural networks, but that's not the first kernel that was linked to deep neural networks. The first type of kernel that was observed, linked with kernel methods, is what's called the convergence of deep neural networks to Gaussian processes at initialization in the infinite width limit. So the infinite width limit is the limit when the number of neurons in all of the hidden layers grows to infinity. And in this limit, if we initialize the parameters as IID Gaussians, then it turns out it was proven that the pre-activations, so the pre-activations of all of the layers in the neural networks, converge to IID Gaussian processes with the covariance given by a kernel sigma. And this kernel sigma L can be defined recursively according to this formula. So we have the formula for the covariance of the first layer, and then the subsequent covariants are defined recursively. And these kernels will play a role later on. That's why I defined them. And of course, because we define the output of the network to be equal to the pre-activation of the last layer, it means that the network function itself is also asymptotically a Gaussian process. So this was the first connection between neural networks and kernel methods and kernels in a sense, but this only describes what's going on with deep neural networks at initialization. What we are really interested in with neural networks is what's going on when you start to train them. And in 2018, we introduced the neural tangent kernel, which allows you which is a new kernel that allows you to describe what happens during training. So during training, let me first define what I mean by training. So first we have a training set of size n, a number of inputs and outputs, multidimensional inputs and multidimensional outputs. And then we can define, we do gradient descent, or actually in this case, it's actually gradient flow for simplicity on the mean square error cost. And we get this formula for the evolution of the parameters. Now, in this formula, if you look to the right, the complex object is really this gradient. This is the gradient of the output of the network function at the training points with respect to the parameters. And this is the kind of difficult object to study, and which makes the analysis of this differential equation difficult. And so the intuition at the time was to say, maybe we don't care so much how the parameters evolve. What we really care about is the evolution of the network function itself. And once you get the formula for the network function itself, by the chain rule, you obtain essentially the same formula, but now we get this scalar product here. This is the difficult object to study. And this can be viewed as a kernel, taking as input x and xi. And that's what we defined at the time as the neural tangent kernel. And the main result about this neural tangent kernel is that in the infinite width limit, so again, we let the number of neurons in the hidden layers goes to infinity, then the NTK converges. So even though it depends on the parameters, and so it's random at initialization and evolves in time, in the infinite width limit, it converges to a deterministic kernel and a kernel that does not depend on time, a time-independent kernel. And we gave a formula for this limiting NTK, which is in terms of the other kernel I introduced before, and this sigma dot kernel, which are also defined in terms of the sigma kernels. It doesn't matter to know exactly that you understand exactly these formulas, definitions for the limiting kernels. And this convergence of the NTK has a lot of impacts on the convergence of deep neural networks. Allowed us essentially to give one of the first proof of led to the first proof of convergence of deep neural networks. Because in our case, actually now essentially the evolution of neural networks suddenly become linear, and so you can just solve in the infinite width limit. You can actually solve the differential equation, just solve the linear differential equation describing the dynamics. And so if we just look at the dynamics of the outputs on the training set, so we have this y theta t, which would be a matrix of size NL, so number of outputs times number of training points. And in this case, it follows the following linear differential equation in terms of this NTK gram matrix. So this is a capital N by capital N matrix, which entries NTK at xi, xj for any pair of point xi, any pair of training point xi, xj. And clearly, with an obvious solution, because it's just a linear differential equation, because now this object does not depend on the parameters or on the output of the network. And so from this solution of the differential equation, it's obvious that what's going to determine the speed of convergence is the eigendecomposition of this NTK gram matrix. And basically, the intuition is that you can also interpret this kind of result, that's a follow-up that we did, in terms of the loss surface. And this result kind of tells us that the loss surface in the small region that you traverse during training actually looks almost quadratic. It's not exactly quadratic, but almost quadratic. And the dynamics are basically the same as up to approximation, the same as the dynamics on quadratic loss, and which is plotted here to the right. And basically we have, if we look at the different eigenvalues and corresponding principal components of this NTK gram matrix, we see that the top eigenvalues correspond to these the direction in the loss where the loss is very narrow, and that's the direction along which you converge very fast. But then you have these small eigenvalues which are in the other direction, which are the direction along which you converge very slowly. And so you can extend, even though this analysis was for gradient flow, you can extend this to gradient descent. And in this case, you will see that it's this condition number, the ratio of the largest eigenvalue to the smallest eigenvalue of the NTK Gram matrix, which is going to determine the speed of convergence of gradient descent trained on these deep neural networks for very wide networks. And so the larger this conditioning matrix, the slower convergence is. And so from all of these results, it's one thing follow that we want. It's in the direction that we wanted to investigate further was how can we use the NTK to better understand certain architecture choice? Because essentially, you can each time you change the architecture of the network, you're going to get a different limiting NTK. And it would be interesting to try to see, oh, this architecture is good because we get maybe this architecture will lead to faster convergence because it leads to a smaller conditioning number of things like that. There's lots of like more practical implications that you can obtain from analyzing the condition number of the NTK for different architectures. And that's exactly what we did. The first architecture effect that we studied was the depth of the network, capital L. And there was already a result that showed that in very deep networks, two regime appears, which were called order and chaos regime. We prefer the name freeze and chaos, but it's equivalent. And so we showed, these two regimes were at least at first observed only for these sigma kernels. But what we did is just extend these results to the NTK itself. Because if we had only the result for the sigma kernel, then it doesn't have a direct implication for the convergence speed. But for once you extend the result to the NTK, then it has direct convergence implications in terms of the convergence speed. And so, assuming that the nonlinearity has a property, this standardized property that we introduced at first, and that the inputs lie on some hypersphere, then there is a characteristic value which is given by this formula, which depends on this balance beta parameter and the nonlinearity, the second derivative of the nonlinearity itself. Then this characteristic value R is going to determine two regimes: the freeze regime, where the NTK or the rescaled NTK converges to a constant, essentially converges to 1. Exponentially fast, you see that this error term goes to 0 exponentially in depth. And on the other hand, if the characteristic value is larger than 1, we get the chaotic regime, in which the NTK converges to a Kronecker delta up to small change. It's not always. If R is larger than 1, there could be some different behavior for when X is equal to -Y. I mean, there's multiple possible choices. It could be either 0, converge to 0, or -1. But in a sense, it's quite rare to have training set where we have one point and exactly the opposite one. So we don't need to care too much about this specific case when X is equal to -Y. That's why we don't take this into account. But yeah, so we get these two regimes, and which are the same. So this transition is exactly at the same point as the transition that was observed in 2016 and 2017 at the time. And the implication that thanks to the fact that it applies to NTK has a number of implications. In the freeze regime, what it means is that since the NTK is almost constant, the NTK Gram matrix is also going to be an almost constant matrix, which with very bad conditioning essentially. So the larger the depth, the larger the conditioning is going to get. So we get an exploding conditioning number, which means an exploding convergence time to get any kind of training. And you can kind of see it, and actually already for small depth on the right, you can see this plot when the depth is just 6, which is really not that deep, and closer to what people use in practice. We see that this blue line would be a neural network, which is typically in this freeze regime. So the NTK doesn't look constant at the time, but you already see that it has a very strong constant component, and that if you look. Essentially, if you take this, actually, you can easily see from experiments that if you, in this setting, if you compute the NTK gram matrix, the dominating eigenvector of the NTK gram matrix is going to be the constant vector, and it's going to dominate the other eigenvalues by a very large margin. And so already such a kernel is going to lead to very bad convergence, even though the depth is just 6. But as the depth increases, then this blue line is going to get more and more constant, closer to a constant, and this gap between the constant mode and the other mode is going to get even always larger and larger, leading to slower and slower convergence. In contrast, if you are in the chaotic regime, which corresponds to the green curve to the right, we see that we get a much narrower curve already for a depth of 6. But as the depth increases, actually this curve is going to get more and more narrow, and it's going to converge to a Kronecker delta. And what this implies is that the NTK gram matrix is going to converge to the identity matrix, which has the best possible conditioning, right? It's a conditioning of just 1, which leads to very fast convergence. But actually, if the kernel converges to a Kronecker delta, then there cannot be any kind of generalization, right? Because essentially, when you feed the data, what's going to happen is that the function that is fitted is going to just be a bunch of Kronecker delta at every training point. But the values outside of the training set are going to be essentially unchanged and still 0. And so there's no possible generalization in this case. And so you can actually show in this case that in this chaotic regime, there's no generalization. And so from this implication, people suggested that people should try to be on the edge between these two regimes for very deep networks. And that's definitely true for very deep networks. And so, for example, if you take a ReLU network without bias, so if beta is equal to 0, then you are exactly on this at the edge between these two regimes. But actually, in this case, the NTK converges to the identity plus a constant. So it converges to the Kronecker delta plus a constant. So it's still not clear that you would get much better generalization in the very deep case. And so in some sense, maybe we shouldn't talk too much about this. I mean, it's interesting to try to understand what's going on in this very deep case, but maybe it's more interesting what this characteristic value tells us for smaller depth. And maybe we should think more of this characteristic value as an indicator of how narrow the NTK is. So essentially, or in some sense, what's the correlation length of the NTK? You see that if you have a very large characteristic value, so in the chaotic regime, you essentially have a very small correlation length after just, so this is the angle between two samples. You see that after just an angle of 2 radians, there's almost no correlation between, no relation between what's going on at this training point and this training point. So in a sense, it describes the correlation length, whereas the correlation in the other regime are very wide. A bit like this, the length scale parameter, which is typical in traditional kernels that people use, such as RBF kernels or others. And so that was the intuition that we had, trying to understand the characteristic value as a different notion of length scale. And so in this case, it makes sense that depending on the task, you would want to have just exactly the right length scale. And so you would want to move from closer to the freeze regime or chaotic regime, depending on the task you're trying to solve. And there's always an easy way to move towards the freeze regime, because you can always increase the bias term, and then this would lead to reducing the characteristic value, and so going towards the freeze regime. But it's not always possible by reducing these beta parameters, you're not always going to be able to reach the chaotic regimes. For example, if you have a ReLU nonlinearity, then it's actually impossible to have a characteristic value which is larger than 1, because the characteristic value is given by this formula. And so our question was that trying to see some other tools that we could use to move towards the chaotic regime, in this idea that maybe for some settings you would want, and we will give one example of a case where we want to be in the chaotic regime later on. what are the tools that we can use to move towards a chaotic regime. And the tools that we identify is what we call normalization in the general sense. So we first defined what's called normalizing the nonlinearity. So the idea is to change the nonlinearity to just translate it and scale it so that the nonlinearity would be centered and standardized on Gaussian data. So this is just the translation of the nonlinearity. And what we show then is that as long as the nonlinearity is not equal to the identity, then after applying this normalization of the nonlinearity, the characteristic value is always going to be in the. You can always find the characteristic value as long as this beta is small enough. We can find the characteristic value will be in the chaotic regime. And so essentially by applying this normalization, you can guarantee that with any if you start with any nonlinearity sigma, just by applying this normalization, you can guarantee that you will be able to reach at least the chaotic regime. And that's basically how we computed, in this case, actually, these plots were all with the ReLU. It's essentially the blue one was with the ReLU, but with a large beta parameter. This one was the ReLU, the orange one was with the ReLU, but with a very small beta parameter. And to be able to compute this green case, we needed to add to use nonlinearity normalization, so to use the normalized ReLU to be able to reach this chaotic regime. And what's interesting is that this normalization of the nonlinearity is actually asymptotically equivalent to layer normalization. And so it implies that layer normalization, which is which is a widely used tool in the architecture of deep neural networks, seems to have this chaotic effect of moving the networks towards the chaotic regime. And so, and it kind of makes sense because it was one of the motivation for layer normalization is to make training faster. And if layer normalization has a chaotic effect, then obviously it's going to make training faster. And so it could be, this could be seen as an explanation for why layer normalization is useful. But there's another type of normalization which is more widely used, which is batch normalization. But maybe if you have tried to work with batch normalization on the theoretical level, then you know that's very difficult to analyze batch normalization theoretically. And so we only have a partial result which suggests that batch normalization has a similar effect. Namely, we show that basically with batch normalization, the constant mode of the NTK, which was this mode that was always dominating in the ordered regime, essentially batch normalization allows you, if you apply batch normalization after the last nonlinearity, then it will essentially control the constant mode and avoid this constant mode from exploding and completely dominating. And so that's a partial answer. And at least empirically, we observe that if we compute the NTK with batch normalization, we see that it has, in a sense, it's even a stronger chaotic. It seems to be like a stronger chaotic effect than layer normalization, which is this green one, or equivalent to layer normalization, this green one. So it seems to be in line with the result, but we don't have a complete theoretical explanation for the chaotic effect of batch normalization at this point. So that's the picture for fully connected networks. And so it kind of gives an explanation for why normalization methods leads to faster training, and suggesting that it's related to a chaotic effect of normalization. But I was actually, in a sense, almost the starting point of this inquiry was I was trying to train generative adversarial networks, and generative adversarial networks are very hard to train. And it seems it's kind of accepted knowledge that you really need to have batch normalization to train GANs, these GANs. And so I wanted to understand why batch normalization is so useful. And so now that we have a basic picture of why, what's the effect of an explanation for why batch normalization, or at least layer normalization, works, I wanted to try to understand what's going on with GANs in this context. And so let me first introduce GANs. So GANs are a model whose goal is to generate, so assume you have a lot of images of faces of humans, for example, a lot of pictures of faces, then you would want to train a network to generate new face that seems to look from this as if they were coming from the same data set, but are actually different from the training data that you have. And the way you do that is that you want to train a generator, G, which receives a random code Z, so which is just a vector of random Gaussian values. And it's a neural network that will take the Z and output of an image. And basically, by changing the parameters of G, you're going to be able to change what the images are generated from this random data. And so to generate a new image, you just need to sample a random code Z. But the difficulty is that how do you choose the parameters of G? And to do that, you rely on a discriminator. So the discriminator is going to receive data generated from the generator and some real data and try to classify one from the other. And then the generator is, the way you train the parameters of the generator G is that you try to modify the parameters so that it will be able to fool the discriminator and become undistinguishable from true data. And then the thing is that it's a very complex dynamics we have because you have these two networks that compete against each other. And so it's much more difficult to study convergence speed and so on because you can get into these kind of oscillations and so on. And a big problem in this training of GANs is the problem of mode collapse, where the generator becomes constant. And basically, you can kind of see and get the intuition from what I talked about before is that this mode collapse should be related to the freeze regime, right? Because freeze regime is characterized by this constant mode dominating. And so in the freeze regime, the generator will, if the generator lies in the freeze regime, the generator will naturally be attracted to constant, to become constant. And this is exactly what happens in mode collapse. And you can actually you can observe this empirically with some picture. So this would be a GAN case. So the true data is the green ones. So you want to generate data in this, you have these five modes, essentially, 5 different Gaussians. It's a mixture of 5 different Gaussians. And the blue ones is the generated data by the generator. And we want so we're going to train this GAN. This is going to be a GAN, and we were going to see how the generated distribution evolves in time. And what you see is that essentially because it's in this case, the generator was in the freeze regime, it can only change the training data in a constant directions. So at the end, it's able to avoid this issue, but you see that it gets stuck for a very long time in this, only moving the generator in a constant manner. And it takes a long time to be able to actually generate data which has lots of variability. And so this was a very small example. So we didn't actually get mode collapse because usually in mode collapse, the network is going to actually be stuck. It's never going to be, it's not like you just can wait longer. Or maybe if you train a huge amount of time, maybe at some point it will be able to learn things. But typically in practice, it's when you can get these mode collapse are just where it's just, you cannot learn anything. It's not sufficient to just wait longer. Maybe this is just because it's a very small example, small dimensional example. But anyway, if we now look at what happens when we change the generator to be in the chaotic regime, we get a very different picture where actually already at first there's more variation on the data. And that this is due to the fact that the freeze and chaotic regime also affect the variance at initialization. And then we see when we train it, we see that directly the generator is able to move different parts of the generated data in different directions. It doesn't move in a constant direction. And so it's able to fit the data very fast, much faster than in the chaotic regime. And so even though we were not able to give a complete proof for why you would observe mode collapse in the freeze regime, this is a pretty good suggestion for why mode collapse appears, that mode collapse is really related to the freeze regime. And so this suggests solutions for mode collapse. The first one, which was already known, is to just use batch normalization because it reduces this constant mode in a sense. But actually what you could also just do is just use either layer normalization or non-linearity normalization, since they are equivalent, or any other way you can find to move to the chaotic regime. And that's exactly what we did in the 2 previous videos I did, and you can see that the chaotic generator was much better at avoiding mode collapse. So that's what you can say about mode collapse for this. When you have only when the data lies on a plane, but things get more interesting when you have more structure to the generator, because typically what the GANs are used to generate images, and in this case, the generator has an extra structure where the generator is a deconvolutional network. And what we did is that, because we were interested in this case, we were able to observe another link between freeze and certain phenomenon in GANs, which is that if G is a deconvolution network, we computed the same freeze and freeze and chaotic regime, and so the chaotic doesn't change much, and so I didn't put anything about it on this slide. But the freeze regime becomes very interesting. So it's a bit more complex, because now the generator has multiple outputs, and the outputs can be correlated. So in this case, the NTK is defined on 2 different inputs, X and Y. The inputs would be, for example, these random codes, Z, right? These random vectors with IID Gaussian entries. But then now you also have correlation between different pixels. So you start from this, you take this random code, generate an image, and the NTKs also computes how the training at different pixels of the output image is going to be affect each other. And we see again in this freeze regime, we observe this in the same way as in the other one. We see that what the NTK converges to is independent on X and Y. So in the sense, it's constant with respect to the inputs, but it's not constant with respect to the 2 pixels P prime. So it's a bit of a complex relation, which depends on this V value, which is the maximum value, such that the stride, so the stride is how much the number of pixels is multiplied after each deconvolutional layer. So this stride to the power of V divides P prime. You don't need to understand exactly the formula, but what's interesting is that if you take an NTK which looks like this, the limiting value here, what you will get is that the dominating modes are not. It's not only going to be the constant mode, because now there's multiple constant modes, right? You could have constant because the generator could generate always the same image, but it could be any image that it always generates, right? So there's a dimension. The constant modes now span a space which is the same dimension as the space of images. And now we're going to get some kind of hierarchy between constant modes, where because of this structure, actually the dominating constant mode is going to be the one which is actually constant in the image. So that generates just the same value on every pixel. Then the next one is going to be the one that are checkerboard patterns, which are images that repeat every 2 pixels. And then the next one are going to be higher order checkerboard patterns, which repeat every 4 pixels, and then 8 pixels, and so on and so forth. And this is an issue, because it leads to you don't want to see these checkerboard patterns in practice. But what's nice is that it's actually the same solution of patch norm and or either going to the chaotic regime, or it's actually layer normalization. And you can really see this in practice if you plot the top eigenvalues, or in this case, in a sense, eigenimages of the generator, of the NTK of the generator. You see that the different 4 lines are 4 different random codes that we've inputted, and we see that we observed in the freeze regime, we observed that it's constant with respect to inputs, because each of the line corresponds to a different principal component, and we see that in all cases we see the fact that it's constant with respect to inputs, in contrast to the chaotic regime or with patch norm, where we have where the dominating principal components are not constant with respect to inputs. But then if we also look at what it looks like inside of the images, we see in the freeze regime, we see this hierarchical structure where we have this first dominating eigen image where the image are essentially constant throughout the image. It's not exactly this, but because it's all red, it's essentially all a constant image. And then the next three ones are the ones that repeat every 2 pixels. If you zoom in, you can kind of see it, that the next three images repeat every 3 pixels. And then the next one repeat every 4 pixels and so on and so forth. And if we then and this doesn't appear at all in the chaotic or batch norm regime. And so, and you can actually see if you then train these networks, train again with these different structures, then you can see that you will end up with these both mode collapse. So the fact that it always generates the same image, and the image that it generates is actually features this same checkerboard artifacts, this same kind of repeating patterns. And if we go to the chaotic regime, or if we add batch normalization, we're able to actually get some nice images of faces, nice generated images. So to conclude, so thanks to the NTK analysis, you can analyze different architectures according to what are the dominating eigenvalues. And so we observed in fully connected network, we observed that there's a regime, this freeze regime, which is where the constant mode is going to dominate the eigenvalue. And actually, if we look at deconvolutional networks, then it's not only constant mode, but checkerboard patterns that dominate the NTK gram matrix. And these dominating eigenvalues, dominating principal components, have problem of both slowing down training, and in GANs, it's not only slowing down training. In some cases, it seems that it just makes training impossible because of this mode collapse. And so it's interesting to see how we can use the NTK to identify these dominating eigenvalues. So we can essentially predict not only that there will be mode collapse, but also what this mode collapse is going to look like, because we can predict these checkerboard patterns from the NTK. and using the NTK, we can then find ways to change our architecture to avoid these problems. Thank you.